A2 Unit 2 Topic 7 is on amines. Amines are derivatives of ammonia. One or more of the hydrogen atoms in ammonia are replaced by alkyl groups. The amines produced can be primary, secondary or tertiary depending on the number of hydrogen atoms replaced. In the glossary you will find definitions for a primary amine, a secondary amine and a tertiary amine. Amines can be named in various ways, all of which are correct. Some nomenclature systems suit certain amines better than others. For basic amines, we use the nomenclature alkyl amine. The example shown here is propylamine. However, the alkylamine naming system is a UPAC naming system. Therefore, this would be called propan-1 amine. This slide shows some of the different names that can be given to primary amines. This table shows how to name secondary and tertiary amines. If a substituent group is bonded to a nitrogen atom, the prefix N is used, as in N-methyl-methylamine. N, is used for two substituent groups. These are in a place of the numbers which cannot be used as the N atoms are not part of the carbon chain. We will also look at aromatic amines. Here's the example phenylamine, which is more commonly known as aniline. Hydrogen bonds exist between amines. The lone pair in the nitrogen atom can form a hydrogen bond with a hydrogen atom in another molecule. This affects the boiling point of amines and their solubility in water. Short chain amines are very soluble in water as they can form hydrogen bonds with water. The solubility of amines in water also decreases from primary to secondary to tertiary amine. The basicity and the reactivity of amines depends on the lone pair on the nitrogen atom. The availability of the lone pair depends on the groups attached to the nitrogen atom. Alkyl groups push electrons in a bond away from the alkyl group. This means the alkyl groups in aliphatic amines push electrons toward the nitrogen atom, which destabilizes the lone pair and makes it donate more readily. The more alkyl groups, then the greater the effect. If we have a look then at aromatic amines, we see the opposite effect. The lone pair of electrons on the nitrogen atom can be delocalized as part of the pi delocalized system in the benzene ring, and this means they are more stable and less easily donated. So phenylamine is a weaker base than ammonia and primary amines. Amines which dissolve in water produce weak alkaline solutions. Amines also react with acids to produce salts. For example, if an amine is insoluble in water, we can allow it to react with an acid to form a salt which will dissolve in water. This slide shows the increasing base strength of amines from primary to tertiary. An exam tip is to know what a base is, which is a proton acceptor, and what it depends on, which is the availability of the lone pair of electrons on the nitrogen atom. This slide looks at the reaction of amines with ethanol chloride and is used to identify an amine. Previously, we saw that amines react with acids to form salts. Ethanol chloride is an acyl chloride, which is a derivative of a carboxylic acid, ethanoic acid. Amines will react with carboxylic acids to form salts. Acyl chlorides are a lot more reactive and the reaction with an amine is very vigorous and hydrogen chloride is given off. The main reason for carrying out this type of reaction is to produce a derivative, in this case N-ethyl ethanamide. This product is purified and its melting point is found. We can then compare that melting point with tabular data, which will allow us to identify the amine that was used. We are now going to look at the preparation of aliphatic amines. Primary aliphatic amines can be prepared by the reaction of ammonia with halogenoalkanes. Because the main amine is basic, the salt is formed. However, the reaction does not stop at this stage and it can carry on. The primary amine can then react with another molecule to form a secondary amine, and the secondary amine can go on to react to form a tertiary amine, and finally the tertiary amine can react further to form a quaternary ammonium compound. In many cases, a good yield of a primary amine is obtained if a large excess of ammonia is used. The reaction of ammonia with a halogenoalkane cannot be carried out by heating a halogenoalkane with ammonia under reflux, as ammonia gas would escape. It is normally carried out by heating a solution of the halogenoalkane and ammonia in ethanol in a sealed tube. Ethanol is chosen because both the halogenoalkane and ammonia are soluble in ethanol. Amines can also be produced by the reduction of nitriles with lithium tetrahydroaluminate 3, otherwise known as lithal. This is represented by, the reducing agent is represented by a hydrogen in brackets in the equation. The nitrile is refluxed with lithyl in dry ether. Amines can also be prepared from amides. Amides contain the functional group CONH2 and they may be reduced by refluxing with lithium tetrahydroaluminate 3 in dry ether. Phenylamine is prepared by the reduction of nitrobenzene using tin and concentrated hydrochloric acid. This is the only time on the A-level course that we do not use the lithal as a reducing agent. In this preparation, phenylammonium chloride, the salt, is formed in the presence of hydrochloric acid. The free amine needs to be liberated using sodium hydroxide or potassium hydroxide. Amines react with nitrous acid and hydrochloric acid to form diazonium ions. Aromatic diazonium ions are stable at low temperature, but aliphatic ones are not and they decompose readily. The diazonium ion is stabilized by the benzene ring. Nitrous acid is very unstable and is generated in situ. We do this by adding hydrochloric acid to sodium nitrite. This reaction is normally carried out below 5 degrees. As mentioned previously, the diazonium ion formed from ethylamine is not stable at any temperature and breaks down to form ethanol and nitrogen. The benzene diazonium ion is much more stable, but again will decompose at higher temperatures. A coupling reaction is a reaction in which two benzene rings are linked together through an azo group. The benzene diazonium ion, which we made previously, will react with activated benzene rings. Although a benzene ring is electron rich, the benzene diazonium ion is not sufficiently electrophilic enough to attack it. If an OH or an NH2 group is attached to it, the benzene ring is activated. Phenol has an OH group, which is electron donating and increases the electron density on the benzene ring. The phenol is used in alkaline solution because the phenolate ion forms that provides even more electron density. Coupling reactions are very sensitive to the pH of the reaction mixture. The benzene diazonium ion normally couples in the para or the position 4 in the ring. This is because the ion is large and there is less steric hindrance. The products from the coupling of benzene diazonium ions with both phenol or phenylamine are coloured. The reason is the extensive delocalization of electrons in the molecule. The azo group has p orbitals which allow the delocalization of the benzene rings to be extended over the whole molecule. Many dyes and indicators contain an azo group. Other reactions of the benzene diazonium salt are based around the fact that it is unstable when it is heated. If we dissolve it and warm the solution above 10 degrees, the benzene diazonium ion breaks down to form phenol. If we warm the benzene diazonium salt in a solution of potassium iodide, we can form iodobenzene.